This fluid mechanics lecture is focused on the equation of motion, which we will derive by applying conservation of linear momentum to a fluid control volume. We will also talk about the appropriate boundary conditions to apply at fluid interfaces. So everyone recalls Newton's second law of motion, which applies to a solid particle. The sum of the forces, F, acting on the particle or object is equal to the mass of the object multiplied by the object's acceleration. In other words, the sum of the forces is equal to the mass times the temporal rate of change of the velocity. Or, most generally, the sum of the forces acting on an object are equal or is equal to the rate of change of the momentum of the object. And the momentum is simply the mass times the velocity vector, v. So we want to apply Newton's second law to a material control volume surrounding a fluid parcel. So to designate this control volume is V sub m. The m means material, and this volume can change in time. As one may recall, a material control volume is one that always contains the same fluid particles. In other words, the velocity of the surface bounding the material control volume is everywhere equal to the local fluid velocity. So denoting the surface velocity as Vs vector, we can say this must be equal to the fluid velocity, which we designate as the vector u. So a representation of our fluid control volume is shown here at the right. So it's an arbitrarily shaped region surrounding some amount of fluid. It's a material volume, so it always contains the same fluid. So Vm of t is the volume. The surface area that bounds this material volume is Sm of t. We're in the presence of a gravitational field, so we designate that with a gravitational acceleration vector g. The fluid has local velocity u, which depends on position x and also time. The surface of the control volume has local velocity v sub s, which also depends on position and time. And as we mentioned, because this is a material control volume, the surface velocity is everywhere equal to the fluid velocity, so Vs is simply equal to u. That's an important point. So a couple of other things to note. The density of the fluid is designated by rho. And rho is simply the mass of the fluid in a given volume. And of course we take this in the limit that the volume becomes very small to talk about the density at a given point. The density can vary with position. It can also depend on time if the fluid's expanding or being compressed. We also worry about the momentum density. So the regular density, or the mass density, is mass per volume. Momentum density is simply momentum per volume. So momentum is just mass times velocity per volume. So we can simply separate this out as mass per volume multiplied by the velocity, and we get rho mass per volume times the velocity of the fluid, which is the vector u. And then the total amount of momentum in the control volume is simply the integral of the momentum density over the control volume. So we have the triple integral over the volume Vm, that depends on time, of the momentum density, rho u dv. And for notational convenience, we'll call this quantity P vector. So the vector capital P represents the total momentum contained within this fluid's control volume. The next step is simply to apply Newton's second law to the fluid control volume. We can say the rate of change in the momentum is equal to the sum of the forces acting on the fluid in the control volume. So I can write this out because this is important. Alright, so we have the time derivative of P is equal to F, the sum of the forces. As we previously discussed, the fluid exerts or is subject to both surface forces, which we denote by F sub s, and body forces, or forces per volume, that we denote by F sub v. And as we showed in the previous lecture, the surface forces are the surface integral over the surface area Sm of t of the stress. The stress is n dot sigma ds, where sigma is the stress tensor. So this integral represents the stresses, or the forces acting on this control volume due to stresses from the fluid outside the control volume. Why is it outside? Well, if you recall, n dot sigma is the stress exerted at that location by the material towards which n points. And n here by convention is the outward unit normal vector. It points to the fluid outside of the control volume. And so this term here represents the sum of all the forces acting on this control surface due to the fluid surrounding this control volume. And that's why we have a positive sign here. Rate of change in momentum is equal to the sum of the forces acting on the control volume. This is exerted by the fluid outside the control volume towards which n points, and therefore it's a force being exerted on the control volume, and therefore a positive sign. Then the body forces, F sub v, the forces per volume, we saw previously, were equal to the volume integral of rho g dv. And if we had polarized or charged fluid, we could also have potentially the force due to an electric field. That's a generalization we leave for specific applications. We're not going to consider that in detail in this course. We'll only worry about gravity as a primary body force. If something is being rotated rapidly, you can also have centrifugal forces that also play a role, and those can be dealt with on a case-by-case basis as needed. So the next step is simply to substitute for the total momentum in this control volume, which is just its integral here. So this left-hand side becomes the time rate of change of the volume integral over Vm of t of total momentum rho u dv, and that's equal to the sum of the forces acting on the volume. So we have the surface forces or stresses, which is a surface integral of n dot sigma, giving the stresses exerted on this control volume by the fluid outside of the control volume due to its deformation or motion. And then we have the body force, or the force per volume, acting on Vm of t which is just the total force due to gravity, which is the integral of rho g over the volume dv. So what we have here is an integral form of conservation of linear momentum in a fluid. Now what we want, for most of our purposes, is a differential statement of the same thing. We want to obtain a partial differential equation valid at every point in the fluid domain that expresses conservation of linear momentum. Whereas what we have so far is an integral expression expressing total conservation of linear momentum for this entire fluid control volume. So in order to get to our partial differential equation, known as a conservation equation for linear momentum, what we want to do is combine all of these terms into one volume integral. So we need to move the time derivative inside, which we can do using the Reynolds transport theorem, or the Leibniz formula, which we discussed previously. We need to convert this surface integral to a volume integral, which we can do by using the divergence theorem that we discussed in the previous help session, and then combine everything into one large volume integral. Once we do that, we can shrink the volume integral down about any arbitrary point x within this control volume. And we can let, therefore, the control volume go to 0 about that point x. Because the point x is arbitrary, and because the actual shape of the control volume is also arbitrary, the only way this combined volume integral will be 0 for any choice of position in this volume and for any choice of control volume is if the integrand vanishes at every point within the fluid domain. So we can then prove the integrand of that volume integral must vanish at every point in order for the integral to be 0 regardless of what point or control volume we choose. And as a result, by setting the integrand equal to 0, we will obtain a partial differential equation expressing conservation of linear momentum at each point in the fluid. Once we formulate appropriate boundary conditions at interfaces between fluids and solids or fluids and other fluids, we can then solve this equation for various prototypical fluid flow problems. So that's what we'll do on the next page. So the first thing we'll do is just recopy this expression. So we have the rate of change in time of the total momentum in the fluid control volume, rho u dv, and this is equal to the sum of the forces acting on this fluid control volume. And we'll spread this out a little bit, call this, these are the surface forces over the surface area S with the subscript m meaning material control volume. Once again, the control volume always contains the same fluid particles, and this allows us to directly apply Newton's second law from classical mechanics, which applies to rigid or solid bodies, directly to the fluid, because the fluid contains the same mass, so there's nothing new in terms of the physics, and Newton's second law applies directly. And so here we have the body forces, which in other words are just gravity. Okay, in order to convert this expression to a volume integral, in other words to bring the time derivative inside, we can apply the Reynolds transport theorem, which is also known as the Leibniz formula for differentiating integrals. And as you recall, there are two components. The first, we bring this time derivative inside. We have the volume integral of the time derivative of the integrand, which is rho u dv. Now it becomes a partial derivative because rho and u can both depend on position as well as time, whereas once you've integrated rho u over the volume, you have something that only depends on time. So this total derivative becomes a partial derivative when you bring it inside the integral. So we've taken into account one of the time dependencies of this integral, namely the time dependence of the integrand rho u. But we've also explicitly shown the time dependence of the domain of integration Vm of t. So the second term in the Reynolds transport theorem accounts for the change in the control volume with time, which can then also affect how this total integral depends on time. So the second component here is plus the surface integral of n dotted with the velocity of the control surface, which is Vs, but Vs is just equal to u, the fluid velocity, since it's material control volume. So n dot u, and then we keep the integrand rho u ds. So the first term takes into account the time dependence of the integrand itself, the momentum density rho u. We integrate then that time variation over the control volume. The second part corresponds to the change in this integral in time due to the change in the volume over which we're integrating. And that's where we get this additional term that has to do with the surface integral based on essentially how rapidly the surface of the control volume is increasing or decreasing. This is like the outward velocity of the surface, and therefore this is how fast the volume of the control volume increases or decreases multiplied by the momentum density. So that's the second contribution we get. We prove that when we derived the Reynolds transport theorem several lectures ago. Or if you like, you can just take it on faith and apply what's known as the Leibniz formula, which is the same thing, and that applies not only in the context of fluid mechanics, whereas the Reynolds transport theorem is really specific to fluid mechanics. But that or the Leibniz formula tell us exactly the same thing. Alright, so then we can take this, the surface stresses here, and we can apply the divergence theorem to this. And so the left-hand side, the rate of change of momentum, is then equal to the sum of the forces. The divergence theorem converts a surface integral of n dot something to the volume integral of the divergence of that same thing. So in other words, this becomes the integral over Vm of t of the divergence of the stress tensor sigma dV. And then finally we just bring down the gravity term as written. Next thing we can do is just rewrite this integrand a little bit. So it's n dot u rho u. The order of the scalar rho is arbitrary, and so it looks a little bit nicer if we write this as n dotted with rho u u. So we preserve the order of the vectors even though u is the same, so u and u stay the same way. And the scalar rho we can put in front, in the middle, or at the end because we're taking the dot product with a scalar, or dot product with a constant vector n. And as a result, this is the exact same thing. So finally, we can convert this surface integral that we obtained from the Reynolds transport theorem into a volume integral by once again applying the divergence theorem. So we can take the surface integral of n dot rho uu ds, and we can rewrite this as the volume integral over Vm of t of the divergence of rho u, not ds, but dv. So now we have the volume integral of the divergence of rho uu. So we have now 4 volume integrals that we can combine into one. So combine all these terms. We'll write one large volume integral we have the partial time derivative of rho u from this term here. We have the divergence of rho u from the second term here. We have del dot sigma, the divergence of the stress tensor. That's on the right hand side. We bring it to the left hand side, and therefore we need a minus sign. So we have minus del dot sigma. And the same thing, we have the rho g brought to the left hand side. We add the minus sign, complete the integrand, dv, and this whole thing then is equal to the 0 vector, since nothing's left on the right hand side. And now we just apply the procedure that I mentioned previously. We let Vm of t go to 0 about an arbitrary point x within the fluid domain. We can choose x and also the shape of the control volume arbitrarily, provided that it's a material control volume. And so the integral will only be 0 for every choice of x about which we shrink it if the integrand vanishes at every point x, because the point x is arbitrary. And the only way to ensure the integral is 0, no matter where we apply it in the domain and about which point we center it, is if the integrand itself is 0 at every point. And so by this argument of letting this go to 0, we can then show this integrand must be equal to 0 at every x in the fluid. So we can then just rewrite this expression. We'll take these two terms here on the left. We have the time derivative of rho u plus the divergence of rho u u, and this is equal to, bring these things back to the right hand side, minus del dot sigma to the right hand side gives us plus del dot sigma minus rho g brought to the right hand side gives us plus rho g. So this partial differential equation must hold at every point within the fluid. Now before we put a box around this and make this, or indicate that this is a very important expression, we can simplify the derivatives on the left hand side by applying the chain rule. So if we take these here, the first term, applying the chain rule, we get rho times the partial of u with respect to t plus u times the partial of rho with respect to t. We can do the same thing with this divergence term. You have to be a little bit more careful because it's a divergence and these are vectors and not just scalars, but the chain rule is quite similar. So the first term we get, grouping rho u together, we get rho u dotted with the gradient of u plus u del dot rho u. If you want to prove this vector identity, that del dot rho uu is equal to the sum of these two terms, you can simply write this out using index notation or Cartesian tensor notation, and you can go through and prove that this expression reduces to this and this. The simplest way to do it is to start with this, write this out, simplify as much as possible, then show that the sum of these two terms, when you simplify them using index notation, is equal to this term. And that will complete the proof. You can also do this component-wise, so you can take the x component of one of the vectors u, for example, and then prove this using that. It makes it a little easier when you only have one vector and then the other components are scalars. You can do this for ux, uy, uz, and add the results together, you prove the same thing. And that's indicated, that proof is indicated in the PDF lecture notes that are available on the website. So finally, I've broken these four terms into two lines for a reason. We can look at the bottom line and we can see there's a common factor of u in front. So this down here becomes u times d rho dt plus del dot quantity rho u. And this expression in brackets should look familiar. And in fact, this is nothing more than the left-hand side of the continuity equation. So this is equal to 0 by the continuity equation. And so what we're left with is rho du dt plus rho u dot del u is equal to del dot sigma plus rho g. So write this out on the next page. It's a very important result. We want to make sure we emphasize its significance. So we have conservation of linear momentum in the fluid gives us rho du dt plus u dot del u, because we brought the rho outside in front, so the rho u dot del u, we bring the rho out, we get u dot del u inside the parentheses, and this is equal to del dot sigma plus rho g. So once again, this equation states that the rate of change of the momentum in the fluid is equal to the sum of the forces per volume. So this term del dot sigma gives us the force per volume due to the stresses from fluid deformation. And the second term is the force per volume due to the body force of gravity acting on the fluid. Now you note that this term in parentheses here also should look familiar, and this is nothing more than the material derivative of the velocity vector u, du dt. So this is the rate of change of the velocity experienced by an observer moving with the local fluid velocity. So in other words, this is essentially the fluid acceleration in a reference frame moving with the fluid, and essentially in a Lagrangian reference frame, but as experienced by someone in an Eulerian frame. So we're changing the fluid acceleration to a stationary observer, and that's why we use the material derivative. So rho times the rate of change of the velocity is equal to the sum of the forces. This is all per volume, because rho is mass per volume. These are surface forces per volume, and this is body force or gravity force per volume. So this is an extremely important equation that should be memorized. You can memorize it in the simplified form: rho du dt, material derivatives, equal to del dot sigma plus rho g, and you should know the material derivative is du dt plus u dot del u. So once again, this is conservation of linear momentum in a fluid. It's also known as the equation of motion, and is also known as the Cauchy momentum equation, after Cauchy, who was one of the first to derive it. So once again, left-hand side is equal to rate of change of momentum per volume, and the right-hand side is equal to the sum of the forces acting on the fluid per volume. So the next step, there are actually two things we need to do to use this to actually solve fluid flow problems. First thing is to introduce a constitutive relation for sigma, the stress tensor, in terms of the rate of deformation of the fluid, Now that's the symmetric part of the velocity gradient tensor. We call that E. For an incompressible fluid. It's proportional to the symmetric part of del U, so it's del U plus del U transpose. That's the symmetric part. That's the rate of deformation or rate of strain tensor E. We've already introduced the constitutive relation for a Newtonian fluid. We'll use that in the vast majority of problems we're going to solve in this course. We'll illustrate that later on. And the second thing we need to do in order to apply this equation to actually solve fluid flow problems is to specify the boundary conditions that must be met at interfaces between the fluid and an adjoining solid, or the fluid and another immiscible fluid phase, so at a liquid-liquid or liquid-gas interface. And that's what we're going to do in the next part of this lecture. So, boundary conditions at interfaces. The case we'll deal with the most in this class is a fluid-solid interface, and so we'll focus most of our effort on this. So at a fluid solid interface, the boundary condition is simply that the fluid velocity, u, is equal to the solid velocity, vs. So we can say u at x is equal to what we'll call x superscript I and t. So x superscript I is the interface location, is equal to the solid velocity, which we call vs, at the same location, which we'll call xi and t. Now usually, unless the solid is deforming, such that it's being stretched or compressed and it's an elastic solid, the solid velocity is usually independent of position. If the plate's moving, the entire plate's moving at the same velocity because it's rigid. And so typically, the solid velocity vs is a function only of time. And in fact, in most cases, the solid's not going to be moving as well, so the velocity will just be zero. But in the most general case, at a fluid-solid interface, we say the fluid velocity is equal to the solid velocity. By convention, this boundary condition is usually decomposed into its normal and tangential components. So for the normal velocity, this gives us what's known as the kinematic condition, or the condition of kinematic compatibility, that we already introduced earlier in the course. We simply take the normal component of this expression up here, which is just found by taking the dot product with the normal vector at the interface. N dot u is equal to n dot vs at x is equal to x interface. This is extremely important. Should be memorized. Now this is known, as well as the kinematic condition, it's known as the no penetration condition. Because in an impermeable solid, there can be no fluid flow through it. And so at an inert impermeable solid, where there's no chemical reaction, the fluid velocity must be equal to the solid velocity in the normal direction. Now this will always hold at an inert impermeable the solid is porous, obviously fluid can flow through the pores, and so this will be different. If it's not inert, if there's a chemical reaction occurring, and it's occurring at a large enough rate, and you don't have an equal, you don't have a balance of a stoichiometric balance in the equation. So if you have, let's say, 3 moles of the fluid reacting to form 2 moles once it reacts to the solid surface, there'll be a net flow to the solid surface due to the stoichiometric ratio of the equation. But in the absence of that, for an inert impermeable solid, the normal component of the velocity of the fluid will always be equal to the normal component of the velocity of the solid. And that's what's known as the no penetration condition. And so we can define the interface, and you can define the normal vector pointing from one to another. So by convention, we typically take the fluid to be phase 1, we can take the solid to be phase 2, or vice versa. We can define the normal vector n, and this tells us the normal components of the interface must be equal. And here's the solid velocity at the interface. So n dot vs must be n dot u. That's known as a no penetration condition. That should be memorized, both the name and the mathematical statement. So that's the normal velocity. We can also then look at the tangential component of the velocity. So the tangential velocity components being equal are what's called the dynamic boundary condition. So we can write this by taking the velocity. We can take u, we can subtract out the normal component, minus n dotted with u. Now the component we subtracted out, that's the normal component of velocity, that's a scalar. To make it a vector again, we multiply again by n, that's the direction of the normal component, is equal to vs minus n dot vs times n, where once again this part here is the perpendicular component of u. So when we subtract out the perpendicular component of the velocity from the total velocity, we are left with the tangential component of the velocity. And so, well, instead of leaving it like this, we can also write it instead as t sub I dotted with u is equal to t sub I dotted with vs at x is equal to x interface. So we will highlight this equation. This expression is known as the no slip condition. We're assuming that when the fluid's touching a solid surface, there's no relative tangential motion. The fluid molecules touching the solid have the same velocity in the tangential direction as well as normal, and the tangential component gives us no slip. So what is Ti? Ti, I can be 1 or 2, is one of the two unit tangent vectors to the interface. So if we look over here at our interface, the tangent vector t, one of them would be like this, let's call it t1. The second one would be perpendicular to the paper. This interface will extend, we're assuming, this direction, so one is in the plane of the paper, the other one is perpendicular to both t1 and n. So t2 is perpendicular to t1, and t1 and t2 are both perpendicular to the normal vector n. So the interface is a plane, or locally planar, it's a surface, and so there are two linearly independent directions you can specify, as indicated, for example, by the direction of these two pens. And so if this flat plate, the paper here, is our interface, the red pen would be one unit tangent vector, the blue pen would be the other unit tangent vector, and then the normal vector will be this black pen, which points out normal to it in the direction shown there. So instead of worrying about what we call the kinematic condition and dynamic boundary condition, they're both good to know, but we typically refer to these, as I mentioned, as the no penetration condition and the no slip condition. Taken together, no slip and no penetration indicate simply that the fluid velocity is equal to the solid velocity at the interface, but as I said, it's customary by convention to separate that condition out into these two, one for the normal component and one for each of the two tangential components of the flow. For a stationary, inert, and impermeable solid, as we said, Vs is equal to 0, and as a result, we get that both n dot u is equal to 0 and t dot u is equal to 0 at a stationary, inert, and impermeable solid. That's the most common case we're going to have, but we will also encounter moving solid surfaces, so it is good to know this more general form of these two boundary conditions. So these are the conditions that should be memorized. We're going to talk about some additional conditions in a few moments, but those are ones you can refer to references to refresh your memory as needed. These are the two that really should become second nature to you. A few comments before we move on. The no penetration boundary condition, stating that the normal components of the velocities in an interface are equal, always holds at a fluid-solid interface unless the solid is porous or unless there's some sort of reaction going on. And it also holds at a fluid-fluid interface for immiscible fluids. The no-slip boundary condition indicates that there is no relative motion or slip when two materials contact one another and are moving. This boundary condition will be assumed to hold for all fluids in this course when viscous effects are included. It may not hold for some polymeric liquids or the moving three-phase solid liquid gas contact line. So for example, if you have water spilled in this plate and the water is expanding and spreading out over it, the question you ask if the no-slip condition holds, how does the water spread over the solid? And several things can happen. One, the contact angle can be very large and it can essentially roll over, and so it can spread by rolling. Second thing that can happen is intermolecular forces such as van der Waals interactions can pull thin layers of the liquid out in front of the bulk liquid, which can then lubricate and serve as a lubricating layer to facilitate the motion. You could also have things known as surface diffusion, which will pull out water molecules in front of the bulk liquid and allow it to flow over as well. Or there can simply be slip at this three-phase contact line where the solid, liquid, and fluid all contact each other in order to allow the contact line to move. We're not going to focus on these particular specialized cases in this course of polymeric liquids or moving three-phase contact lines very much at all, and so the no-slip condition can be assumed to hold whenever viscous effects are included. So you say, well, when does the no-slip condition not hold? Well, if we're considering inviscid or therefore irrotational flows in which viscous effects are neglected to a first approximation, and this approximation can be quite accurate for flows at large Reynolds numbers away from a solid boundary, the no-slip boundary condition may need to be abandoned at a first approximation. We then add a second approximation that will restore the no-slip condition and give us a uniformly valid approximation to the entire fluid flow field. We'll talk about this in more detail when we discuss boundary layer at the very end, boundary layer theory at the very end of this course. But for now, we'll assume the no-slip and no penetration conditions always hold at fluid-solid interfaces. They should be memorized. They're quite simple. They state that at an interface, the tangential and normal velocities on each side of the interface are equal. In general, there are three unknown velocity components, let's say in Cartesian coordinates, ux, uy, uz. The no penetration condition provides one boundary condition, and the no slip condition provides the other two boundary conditions. This is sufficient for a fluid-solid interface. We can now go over an example of this flow. So let's say, example, flow induced by a moving surface. So we can take a surface, we'll draw it over here. This will be our surface. We'll put a little cross-hatching here to indicate that it's a surface, not just a line. And this surface is being moved to the right at velocity v. We'll call this direction to the right. Let's draw this a little better here. This will be the x direction. Y will be this direction. And then we can make z in this direction here. It's a little different than our typical choice of coordinate systems, but still right-handed. X cross y gives us plus z. So in other words, the surface velocity vs is equal to v times ex. The question that we ask are, what boundary conditions should be applied to the fluid, which is, for example, sitting up here above the surface, at the interface with the solid? So I'll give you a brief moment to think about this. Now we'll discuss the answer. So the first thing we can say is, well, what's the no penetration condition? As we stated on the previous page, n dot u is n dot vs at x equals xi. So we have n dotted with u is equal to n dotted with vs at any location along this interface. The interface corresponds to y equals 0. So what is n? Well, n will be the unit vector perpendicular to the interface. We'll point from the solid to the fluid in this case. Here's n. N for this system shown here is equal to EY. So when we write this out, we get EY dotted with, we have UX EX plus UY EY plus UZ EZ is equal to EY dotted with velocity of the surface Vs, which is capital V times Ex. Ey dot Ex is 0, Ey dot Ez is 0, Ey dot Ey is 1, so we get Uy, Ey dot Ex is 0. So this tells us, when we write this out, is that Uy is equal to 0 at y equals 0. So that is the no penetration boundary condition for this example. You can see the procedure is fairly straightforward. You apply the general form of the boundary condition. N.u is n.vs. Just identify what n is for the particular interface under consideration. In this case, it's the x-axis, so the normal vector here is y, pointing into the fluid. We're assuming that this plate extends out in the z direction, like this. And therefore, the fluid lies above it. And so the normal direction is n is Ey. We say that Uy is equal to 0. Now, if you can do this by inspection, you don't have to actually write this out and do every step I showed here. This is just to show you the general procedure for a more complicated case. But in this case, it's pretty obvious, and so you can just state by inspection what the result is if you so desire. Now we can look at no slip. So if you look at no slip, we have the unit tangent vector t sub I dot u is equal to t sub I dot vs at the interface location. So we just apply that here. Ti dot u is equal to Ti dot Vs at interface, which is y equals 0. We can take now our choice of tangent vectors t1 and t2. The choice of each one is arbitrary. As long as you get the two vectors correct, you can label either one 1, you can label either one 2. So let's take t1 to be ex, we'll take t2 to be ez. So if we apply the first one, we get ex dot u is equal to ex dotted with vs, and vs is capital V times ex at y equals 0. So ex dotted with u, this was u, ex dot u just gives us the x component. We get ux is equal to ex dot ex is 1, so ux is equal to v at y equals 0. And this, therefore, is one of the two no-slip conditions for this particular system. The second one, we can just take T2 is equal to EZ, so EZ dot U is equal to EZ dotted with V EX at y equals 0. And so if we do that out, we'll see that the z component of u is uz, ez dot ex is 0, and so uz is equal to 0 at y equals 0. So that's the final component of the no-slip condition for this system. So there's, in general, for 3D flow, there are two no-slip conditions and one no-penetration condition. A lot of the flows we'll talk about will be simplified flows, will be two-dimensional flows, and therefore we'll have one no-penetration and only one no-slip for that particular flow. Okay, so that completes our discussion for fluid-solid interfaces. At a fluid-fluid interface now, let's say we have some curved interface. We have U1 and we have U2. Let's say U2 in Cartesian coordinates is U x2, no vector there, EX plus UY2 EY plus UZ2 EZ. We have the same thing for U1. So the fluid-fluid interface, there are in general 6 unknown velocity components. Compared to the 3 at a fluid-solid interface, because there's 2 fluids, and typically we don't know the velocity in either. So we have 3 components in U2 and 3 components in U1, giving us 6. So no slip and no penetration boundary conditions still apply at the interface. This gives us 3 boundary conditions. We, however, need 3 additional boundary conditions to determine all 6 of the unknown velocity components. And so the question is, how do we obtain these additional 3 relationships? The answer is that we need to balance the stress at the interface, as well as balancing the velocities. In other words, we need to perform a force equilibrium calculation, or a force balance, at the interface to find the remaining 3 conditions that we need. So, let's consider force equilibrium at a fluid-fluid interface. So we'll take a curved interface like this between 2 fluids. So we have fluid 1 and we have fluid 2. And by convention, we're going to draw the unit normal vector n from phase 1 to phase 2. pointing into phase 2 from phase 1. Let's put it that way, at the interface. We will denote the distance along the interface as a stripped L. So that'll be arc length along the interface, L. And then we'll make a small or very thin control volume along the interface. We'll assume this thing has unit length into and out of the board, or in fact we'll essentially just consider a two-dimensional interface for the time being and then generalize it to 3 dimensions. So at the left-hand side of this control volume, we have arc length L. At the right-hand side, we have arc length L plus delta L. So delta L is the total length of our very small differential control volume. In other words, it's the differential arc length from position L to position L plus delta L. If you like, you can call this position A and this position B, and then delta L is just the arc length from A to B along the interface. So we also have normal vector pointing into phase 1, which we'll call N1. And that's just equal to minus our regular N. So if we apply force equilibrium at a test surface like this in the bulk of the middle of a fluid, we found that the stress on the top surface must be equal in magnitude opposite in direction to the stress on the bottom surface. It's Newton's third law, action-reaction. In this case, we have an interface between 2 different fluids, 1 and 2. And as a result, the intermolecular forces between the fluids might not be balanced at the interface. In the bulk of the fluid, a molecule of fluid 1 is surrounded by all molecules of fluid 1. A molecule of fluid 2 is surrounded by all molecules of fluid 2. And so the intermolecular force is essentially balanced. At the interface, however, a molecule of fluid 1 is bounded by molecules of fluid 2 above, and vice versa. And this can lead to unbalanced intermolecular forces that result in what's known as interfacial tension. So interfacial tension is a force per length that's exerted in the plane of the interface. So for example, there's a force being exerted here in this location of the interface. We call this F sub gamma at location L plus delta L. Likewise, there's a force here, and these are tensions, so they're always pulling outward from the control volume. It's just like you have string on both sides. The string is being pulled apart, providing a tension. So here we have F sub gamma at location L. So what is this? Well, F sub gamma is equal to gamma, which is the interfacial tension, multiplied by the unit tangent vector T. So gamma is the interfacial tension, which is a force per length. The length is in the direction into and out of the paper in this particular case for the 2D interface. So it's a force per length. So in this case, it's just a force we add up when we're doing total forces per length acting on the interface. We just take the surface tension multiplied by the unit tangent vector T. So I'll just specify per unit length in the third direction, which is into and out of the paper. We're assuming that just to be unit length, or we're just considering the case of a 2D interface. So now, if we apply a force balance, or essentially a balance of forces per unit length into and out of a paper, we have the stress exerted by fluid 2 on the top of this interface. We have the stress exerted by fluid 1 on the bottom of this interface due to the deformation in each of the fluids. And then we have to account for this tension force, the interfacial tension, due to the unbalanced intermolecular forces at the interface. So the stress, or the force per length in the top surface, is the stress multiplied by the length over which the stress acts, or essentially the length of this control volume, which is delta L. So the stress is N dot sigma. We'll label it as sigma 2 because that's in fluid 2. N dot sigma 2 is the stress. And then we multiply by the length of the control volume to get the force per length. Force per area is stress times length gives us force per length. So the length of this thing is delta L. Then we get plus N1 dot sigma 1 times delta L. That's the force from the deformation of the bottom fluid, the stress acting on the interface. And then now we have to account for the interfacial tension forces. So we're taking L to be positive moving towards the right. So we're going to add interfacial tension, and the direction it acts is in the direction of the tangent vector t to the interface. This is at position B. It's moving towards the right, L plus delta L. Then we have the interfacial tension force on the left, and it's moving towards the left, the direction opposite of increasing L, so that's taken to be negative. So we have minus gamma t at position L. So t is the unit tangent vector, which will point this way and also that way. So that force is opposite the direction of t. That's why I have the minus sign here. And the sum of these forces per length is equal to 0. So we can now say that N1 is just minus our regular defined N, which points from 1 to 2. We can divide by delta L and rearrange this slightly. So we get N dot sigma of 2 minus sigma of 1 plus the surface tension or interfacial tension. It's interfacial tension if it's between two fluids. If it's between a fluid and a gas, it's typically called the surface tension. We'll call this interfacial tension gamma times the unit tangent vector at L plus delta L minus the interfacial tension times the unit tangent vector at position L divided by delta L is equal to 0. We can take the limit as delta L goes to 0, and we find that N dot sigma of 2 minus sigma of 1 plus, in the limit that delta L goes to 0, this becomes the derivative of the product of the interfacial tension and the unit tangent vector. And it's the derivative with respect to arc length along the interface L of gamma times the unit tangent vector t is equal to 0. So what this tells us, I'll put a box around this because this is sort of the important intermediate result for now. It's not the form we're actually going to apply this in for any problem, but it's a key result that shows what's going on with the essential physics. It says that now, with the interfacial tension effects included, there's a jump or discontinuity in the stress or traction across a fluid-fluid interface. Now this derivative term can actually be expanded since it's the product of it's the derivative of the product of two terms. So we get gamma, the derivative of the tangent vector with respect to arc length L, plus d gamma dl times t. And it turns out that dt dl, if you do some geometry, you'll find is equal to minus kappa times a unit normal vector n, where this kappa is 1 over r. R is the radius of curvature of the interface, and therefore the kappa is known as the curvature of the interface. Has units of 1 over length, as indicated by 1 over r. R is a radius, so it has units of length. So basically, we've decomposed this derivative into two components. And so we say the difference in the stress across an interface is equal to the sum of two terms. One is the interfacial tension multiplied by the curvature multiplied by the normal vector, so that acts in a normal direction. We have a part here which is due to the variation of the interfacial tension along the interface multiplied by the unit tangent vector. So there are two different effects. A curved interface can influence this stress balance even if the interfacial tension is constant, whereas a planar interface, there will be no curvature, so this term goes away, but if the interfacial tension varies along the interface, even if the interface is flat, there can still be an effect in the tangential direction. You might say, why does interfacial tension vary with position? Well, it varies with temperature, decreases with temperature usually. It also decreases with the concentration of surfactant, or soap. Essentially weakens the intermolecular forces and lowers the interfacial tension. So if you have the presence of surfactant or soap or some kind of contamination on the interface, or if you have a temperature variation along the interface, these are both known as Marangoni effects, and they can drive Marangoni flows. We'll talk a little bit more about this later when we talk about hydrostatics and pressure with curved interfaces. So this is a quick sketch of the derivation for a two-dimensional interface. We can extend this to a three-dimensional interface to get the most general result, and rather than actually go through and derive it, I'll just state the key result. So extension to 3D is n dotted with sigma of 2 minus sigma of 1, the difference in the stress across the interface, plus 2 stripped h n times the interfacial tension, plus this del s gamma is equal to 0. Del s is defined as identity tensor minus n dotted with the gradient. This is known as the surface gradient operator. This h is equal to minus 1/2 del dot n, where n is a normal vector. And this is known as the mean curvature of the interface. And this term here, this del s gamma, that's essentially the gradient of the surface tension in the plane of the interface, and that can be written as d gamma dl, where L is arc length, multiplied by the unit tangent vector t. So t will be the unit tangent vector pointing in the direction of the most rapidly changing interfacial tension gamma, and this L hat term will be the arc length in the direction of the unit tangent vector t. So this then will be the rate of change of the interfacial tension with arc length in the tangent direction in which it's changing most rapidly. But the easiest way to think about it is a surface gradient. Just says that's the gradient of the interfacial tension along the interface. So we're essentially subtracting out any perpendicular component, but there is no interfacial tension in the perpendicular direction. It's only defined in the plane of the interface. That's why this has to be the surface gradient operator. Now, if the interface is defined as z is some function of f of x comma y, so this gives us the interface location, and this is more for your knowledge than for actually using this in the course. This is rather complicated, but twice h, which is then equal to minus del dot n, ends up being equal to 1 plus df dy squared times the second derivative of f with respect to x minus 2 df dx dy times the second derivative of f with respect to x and y plus 1 plus df dx quantity squared times the second derivative of f with respect to y, all divided by 1 plus df dx squared plus df dy squared, all raised to the 3/2 power. So this is how one would calculate the mean curvature of the interface for an interface that's defined as z is some function f of x and y. Now, not all interfaces can be defined as such. If we deal with a cylinder of radius r, then we find that this stripped h is equal to minus 1 over 2 capital R. If we deal with a sphere of radius r, h is equal to minus 1 over r. It's essentially there's two curvatures, minus 1 over 2r in each of the two perpendicular directions. You add them together, we get minus 1 over r versus minus 1 over 2r for the cylinder. And if it's a planar interface, namely a flat interface, then the curvature is equal to 0. Curvature h is less than 0 if EZ points away from the local center of curvature. In other words, if it's a convex interface, and h is greater than 0 if the opposite is true, namely it's a concave interface. Now, some authors introduce the symbol kappa m instead of h. That's defined as kappa m is minus h as another way of expressing the mean curvature. I like the notation h, but if you see the kappa m, for example, textbook by Pazarkides, note that there's a difference in a minus sign. And so their kappa m is just minus h as defined here. Now, the most important thing is that we can take this general form of the stress balance at an interface, and just like we did for the velocity conditions, we resolved them into normal and tangential components, getting the no slip and no penetration conditions. We can resolve this interfacial stress balance into the normal and tangential components as well. So what we'll do, we'll recall that sigma, the total stress tensor, can be defined as the viscous stress tensor tau minus the pressure times the identity tensor. So we substitute this expression for sigma 1 and sigma 2. Then we take the dot product of the normal vector n with this expression, and we take the dot product of the tangential vector t with this expression. And so we arrive at one normal stress balance and one tangential, or two tangential stress balances, one for each of the two unit tangent vectors, using a very similar procedure to what we did for the velocity boundary conditions. So this is the form we're actually going to use in this course. So the normal stress balance, we simply take the dot product of the normal vector n with this expression here, and what we find is that the variation of surface tension along the interface in the tangent direction drops out. This only has a component in the tangent direction, not the normal direction. This curvature part, however, does have a component in the normal direction, so that remains. And then here, this is a stress. We take the dot product of n with this a second time. That gives us the normal component of the stress. And therefore, that gives us what we call the normal stress balance. We're balancing the stresses in the normal direction. So once we do that, normal stress balance, this will often be abbreviated as NSB. What we find is that the pressure in fluid 1 minus tau NN in fluid 1 is equal to the pressure in fluid 2 minus tau NN in fluid 2 plus 2 gamma times kappa m. Or if you want to use this in terms of h, it's minus 2 gamma times the script h. So this gives us the normal stress balance at a fluid-fluid interface. What is this 2 kappa m term? 2 gamma kappa m. It's known as the capillary pressure. From the product of the interfacial tension and the interfacial curvature. So for example, if you put a drop of liquid on a surface with a groove, you'll see the liquid moves along the groove. And the reason it does that is because of capillary pressure. There's a curvature of the liquid at the front. The curvature changes the pressure, it lowers the pressure, and essentially therefore there's a pressure difference between the back and front of the drop that pushes it along the groove. The same thing can happen if you have a very thin tube immersed in a container of fluid. So let's say we have a container of liquid. We put in this very thin capillary tube or very thin straw. The question is what happens? Well, you'll find you have kind of a meniscus here that's curved downward, and so in fact the fluid will fill the very thin straw or capillary tube to a height that's greater than the height of the surrounding liquid. You say, why does this happen? Well, if you zoom in on this, here's the top of the thing, of the container. We have a meniscus that looks like this. This type of curvature means that the pressure in the liquid is lower than the pressure at the gas due to this term right here. And because the pressure is lower, the pressure down below is actually higher, and the fluid is essentially pumped up until the weight of this additional column of water balances the difference in pressure due to this interfacial curvature. Now we'll talk more about this in a couple of weeks when we talk about some hydrostatics with interfacial curvature. This is just a very simple example of when this capillary pressure matters. So it matters in small scale systems where there's pronounced interfacial curvature, and in fact for bubbles, droplets, or micro scale flows, this can actually dominate fluid behavior. For larger scale flows, that'll be the focus of most of this course. This term is essentially negligible. It's much smaller than everything else in this equation. If the interface is large, the curvature becomes very small, and this can be neglected. So unless you're told otherwise, you can neglect this interfacial curvature term. So what is tau nn? Tau nn is the normal component of the stress. So it's n dotted with n dot sigma. Recall n dot sigma was F, the stress vector or traction. This is n dot F, so it's a normal component of the stress or the normal component of the traction at the interface. We just abbreviate it as tau nn. In fact, it's not sigma, it's really tau. We're only looking at the viscous component here. We already separated out the pressure part, which is the additional contribution from sigma. So we're only looking at the viscous stress tensor with the tau part since the pressure has been extracted. Why do we break it up into pressure and tau instead of just using sigma? Well, the reason is that tau nn is usually small for the types of flows we're going to look at in this class. So in addition to neglecting the effects of surface curvature and interfacial tension, we can almost always neglect the effects of the normal component of the viscous stress. And so the simplified form of the normal stress balance that we'll use in this course is that at a fluid-fluid interface, the pressure is continuous across the interface. So this is our simplified form of the normal stress balance for this course. The pressure is equal across the interface. And so most likely we'll have a liquid being bound by a gas. We know the gas pressure is typically atmospheric pressure, and therefore the pressure at the surface of the liquid where it's in contact with the gas, this is liquid, this is gas, the pressures are the same at the interface. So that's the form of the normal stress balance we will almost always apply. So if we go back to our general stress balance at the interface and take the tangential component, namely we take the dot product of the unit tangent vector t with this expression for the interfacial stress balance, we arrive at the tangential stress balance, which we'll call TSB. And this will tell us that tau nt at 1 is equal to tau nt at 2 plus t dotted with del s gamma, which we can also write as d gamma d L hat, where L hat's the unit vector along the plane of the interface in the direction of the arc length. So what is this? Tau nt is the tangent vector dotted with the stress. The stress is n dot tau. And what is this term here? Well, this term here, the variation of the interfacial tension along the interface, gives us a shear stress. It's a stress in the that's always parallel to or tangent to the interface, and it's due to what we call Marangoni effect, or it results in a Marangoni flow. Now the interfacial tension, as I mentioned, decreases with temperature. That's known as a thermocapillary flow, and it also decreases with concentration of surfactant. Surfactant concentration, like a soap concentration, we denote by capital gamma. It's also less than 0, and that's a surfactant effect. Now usually surfactant effects are much larger in magnitude than temperature effects on the interfacial tension. Now once again, in almost all cases in this course, we can neglect the contribution from the variation in surface tension along the interface. In most problems that will be small or actually 0. And so we can once again use a simplified version of the tangential stress balance in this class, which will be T n t in 1 is equal to tau n t in 2. And what this is saying is that the stress that's parallel to the interface is continuous across the interface. This is our simplified tangential stress balance in this class. So to summarize, for most problems we're going to look at, the normal stress balance gives us an expression for the pressure at a fluid-fluid interface, typically a liquid-gas interface, and the tangential stress balance will specify the shear stress at an interface. So we have just enough time to go over a quick example of this to conclude this rather lengthy and detailed lecture. So here is our example. We have an inclined plane like this, a solid surface, so we'll add this cross-hatching. We have liquid flowing down this plane. We'll designate our coordinates. We'll have x in the direction liquid will be flowing down. We will have y perpendicular this bottom surface. We will have unit normal vector n at the interface. Above the liquid we will have air. Pressure will be P naught. And we're given that the velocity u is unidirectional, and it's ux of y only in the x direction. We have gravity acting downward. We're told to neglect interfacial tension in this problem. We'll call liquid phase 1, we'll call the gas phase 2. So ux is given by this, uy and uz are 0. So I want to say, what does a normal stress balance give us? What does a tangential stress balance give us? So the normal stress balance, if we write it out from its general statement, up here we're going to neglect the interfacial tension as we said, so we just have the pressure and the normal components of tau. I'll show you why the normal components are typically 0. So we have P1 minus tau N of 1 is equal to pressure 2 minus tau N in 2. In the system, N is EY. So tau N is EY dotted with EY dot tau. So basically you can just change the N to tau. This will give us tau Y. We can look this up in an appendix of your favorite textbook, for example, Bird, Stewart, Lightfoot, Appendix B1. We find that tau YY is equal to mu times 2 du y dy. Well, uy is equal to 0. So that's equal to 0. And tau YY is equal to 0 in both of these terms. 0, 0. And so, as a result, what this tells us is that the pressure in liquid 1, or in fluid 1, at the interface at y equals h, is equal to the pressure in fluid 2 at y equals h. And the air has atmospheric pressure, basically everywhere, right up to the interface, and so this is equal to P naught. So the conclusion is that the pressure in a liquid P1 at y equals h at the interface is equal to P naught. So the normal stress balance, as we said, reduces to a specification of the pressure at the interface between the liquid and the gas. That's what we get. So then we say, well, what does the tangential stress balance give us? And this one we'll go through in a little bit of detail because it's important. The conclusion is the key important thing here, tangential stress balance. Well, we say, going back to our general statement here, we're neglecting interfacial tension, so tau nt at 1 is equal to tau nt at 2. That's our tangential stress balance. So tau nt at 1 is equal to tau nt at 2. We already saw that n is equal to EY. The question is, what is the tangent vector? Well, tangent to this interface is in the plane of this blue line. That's pointing in the x direction. So the tangent vector is equal to EX. And so now what this reduces to is that tau n is EY, so tau yx in 1 is equal to tau yx in 2. And now we can once again just look up what these expressions are for tau yx, for example, Appendix B of Bird, Stewart, and Lightfoot. So what we get, substituting here, and that's where we apply essentially our constitutive relationship. We're relating to this stress to the rate of deformation, or essentially we're relating the stress to the velocity derivatives. We find that tau yx, 1 is the liquid, so we get mu liquid times, and then this tau will be duy liquid dx plus dux liquid dy, evaluated at the interface, which is y equals h, and that's equal to the same thing written for the gas, mu gas times duy dx in the gas plus dux gas dy at y equals h. So uy in the liquid is 0. It's unidirectional. We can assume that uy in the gas then is exactly the same. It's also equal to 0 because in fact the normal components of the velocities have to be equal across the interface from our no penetration condition. So if uy in the liquid is equal to 0 at the interface, uy in the gas is also equal to 0 at the interface. So uy in the liquid is 0 because it's unidirectional flow. We're given this information. And then uy in the gas is equal to 0 from application of the no penetration condition. So we can then rearrange this, and we find that dux in the liquid dy at y equals h is equal to mu gas over mu liquid times dux gas dy at y equals h. What we'll find is the ratio of the viscosity of the gas to that of the liquid is small. Moreover, this derivative, this velocity gradient in the gas is smaller than dux liquid dy. Why is it smaller? Well, the gas extends a much larger distance than the liquid. So in the liquid, the velocity has to go from the interfacial velocity to 0 over the small distance that corresponds to the thickness of the liquid film. Let's say this thickness is capital H. So du liquid dy is roughly u max over h. dux gas dy is roughly u max over something, we call it h gas, and h gas, the thickness of the gas layer, is much bigger than the thickness of the liquid layer. And so we take that ratio, we find that the velocity gradient dux dy in the gas is very small compared to dux dy in the liquid, because the extent of the gas is very large compared to that in the liquid. So the only reason this wouldn't be true is if you had a very thin region of the gas. So say you had a bounding surface right like this. So you had a very thin region of gas next to the flowing liquid. Then the velocity gradient is going to be very large in the gas. It's going to go from the interfacial value, which is equal to liquid value, because that's the no-slip condition, to 0 over a very thin distance. And because that velocity gradient is then so large, this term here would be relatively big, and relatively big times small means something that's important. But in the absence of that, if the thickness of the gas layer is the same as the liquid layer or bigger, which will almost always be the case, then this term here is very small as well. So in other words, the velocity gradient dux dy in the liquid at the interface is a product of two small terms, and therefore it's essentially 0. So the way the tangential stress balance is typically written is dux liquid dy at y equals h is approximately equal to 0. Now this is further generalized, and it's typically written as tau nt. So we're basically saying even though this great velocity derivative is 0, it's often just then multiplied by the viscosity again to give us the stress. And so often it's written as the tangential component of the stress is equal to 0 at a liquid gas interface in the liquid phase. So this would typically be tau yx is roughly equal to 0, or mu dux dy is roughly equal to 0 at a liquid gas interface. And what this means is there's negligible shear stress exerted on the liquid by the gas. Basically, the gas viscosity is so small compared to the liquid viscosity, and the velocity gradient in the gas is so small compared to that in the liquid, that the gas exerts almost no shear stress in the liquid at the interface. And so that can be neglected, and this end result can be applied without derivation at any liquid-gas interface in this course. So basically saying zero shear stress at any liquid-gas interface, you can just state that as the tangential stress balance result. You don't have to derive it again like we did here. So finally, to summarize our boundary conditions at fluid-fluid interface, we do is we equate velocities. So u1 is equal to u2, and we can decompose these into normal and tangential components, and so we get no slip for the tangential components, and we get no penetration for the normal component. This is the same as at a fluid-solid interface, so these are the ones that should definitely be memorized. So it holds no slip and no penetration, hold both at fluid-solid and fluid-fluid interfaces. We also equate at a fluid-fluid interface the pressure. So P1 is equal to P2. That's a result of the simplified normal stress balance. And then finally, we can equate the shear stress. And equating the pressure and shear stress at the interface is valid in the absence of interfacial tension effects, which we can assume unless we're told otherwise in this class. So the shear stress in 1 is equal to the shear stress in 2, and that's the result of the tangential stress balance. So in other words, u1 dux dy in 1 is equal to u2 dux dy in phase 2. If it's a liquid-gas interface, we can specialize these three results even further. So we get u liquid is equal to u gas. This is usually not useful because we don't really know what the gas velocity is. What's more important is we find that pressure in the liquid is equal to the pressure in the gas, which would be P naught, and we find that the shear stress, mu dux dy in the liquid is roughly equal to 0. And those are the key results to know. So the ones you should memorize are no slip and no penetration for fluid-solid interface. You should recognize that they also hold for a fluid-fluid interface and understand how to get the no slip, the normal and tangential stress balances in these simplified forms. Namely, the pressure is equal at a liquid-gas interface and there's zero shear stress at a liquid-gas interface. And that's all we really need to know for the purposes of this course. Now finally, for completeness, I will just note that with phase change, so if you have evaporation, condensation, etc., the no penetration condition actually is a little bit more complicated. It becomes N dotted with U minus VI, where VI is the interfacial velocity, times rho in phase 1 is equal to N dotted with U minus VI rho in phase 2. Rho with the density of the fluid in either phase 1 or phase 2. VI is equal to interfacial velocity. So for example, if you have fluid evaporating, liquid evaporating into a gas, the interface might move due to the evaporation process and the change in density. And so this would be the no penetration in the condition in the presence of phase change. Now we're not going to use this actually in this class, but it's here for your knowledge just to recognize that if you do have phase change, you have to use a more complete form of the no penetration or kinematic boundary condition to accurately account for the phase change, and that's just given here for your reference. So the simplified forms of the boundary conditions at a fluid-solid interface without phase change, no slip and no penetration, should be memorized, as well as the simplified forms of the normal and tangential stress balances as mentioned. Normal stress balance being pressure in liquid is equal to pressure in the gas. Tangential stress balance meaning zero shear stress at a liquid-gas interface. So those, as well as no slip and no penetration, should be memorized and become second nature to you. And we'll go through many examples in the next couple of weeks of applying these to solve fluid flow problems, and you'll have also homework problems as well to practice on.